Hello everyone and welcome to Calc Lesson number 39. Today we are going to do our first day of section 3.7, which focuses on optimization. Today we are going to be looking at profit, revenue, and cost examples. One of the most common applications of calculus involves the determination of minimum and maximum values. Consider how frequently you hear or read terms such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, greatest distance, and so on. Section 3.7 looks at many different applications of optimization. Each lesson will look at a different type of example of these problems. Today, we will look at examples of optimization involving profit, revenue, and cost. We will be finding things such as the maximum profit or looking to minimize cost. Ultimately, what we're looking for are minimums and maximums. For each problem today, we will first identify all given quantities and quantities to be determined. Second, we will write or create the equation that we want to maximize or minimize. And then third, we'll use the calculus that we learned throughout all of chapter 3 to determine our extrema. So what that means is we're going to be using our first derivative to identify the x values for which our equation has a horizontal tangent or a minimum or a maximum. From there, we'll plug back into our original equation to actually find what we have as our maximum or our minimum. So let's jump right in. Number 1 says the profit P in thousands of dollars for a company spending an amount S in thousands of dollars on advertising is given to us as, I'm just going to highlight so we don't lose it, P equals negative 1/10 S cubed plus 6S squared plus 400, and that's our profit. We want to find the amount of money that the company should spend. So we want to find S in order to yield a maximum profit. So we want to maximize our profit equation. So they gave us our profit equation P as negative 1/10 S cubed plus 6S squared plus 400. And because we want to find the maximum, we want to use the calculus we know. So we want to take the derivative and then look for those critical points where we have those horizontal tangents. And then from there, we want to plug them back in and see which one is actually the maximum value. So we'll start by taking our derivative, P prime, using the power rule, bringing that 3 in front. We get negative 3/10 S squared plus bringing that 2 down, 12S. Then, of course, the 400 goes away. To find our critical points, or those places where we have that horizontal tangent, we're going to take that derivative and set it equal to 0. So negative 3/10 S squared plus 12S equals 0. Lots of ways to solve this. I hate that fraction, so I'm going to go ahead and get rid of it by multiplying my whole equation by negative 10/3. So I have S squared. 12 times negative 10/3. 12 divided by 3 is going to be 4, so I have minus 4 times 10 would be 40. S equals 0. Taking out my greatest common factor, which is S, I'm left with S minus 40 equals 0. So I get S equals 0 and S equals 40. So those are the two places, or the two values, where my profit equation has that horizontal tangent, meaning those are likely my relative extrema. What I want to do is actually plug them back into the original profit equation to see what the profit is at each of those spending amounts. So if we look at the profit when we spend $0,000, we have negative 1/10 times 0 cubed plus 6 times 0 squared plus 400. Gives us 400, and remember this is in thousands. If we look at 40, we get negative 1/10 times 40 cubed plus 6 times 40 squared plus 400. And just being careful as we go through, 40 cubed times negative 1/10 should give me negative 6,400. Plus 40 squared times 60 should give me 96,000. plus 400. So P equals 40 gives me 90,000. So comparing our two extrema, 400 is obviously smaller than 90,000. So P of 40 is the maximum. And then we just want to make sure we answer the question correctly. Find the amount of money the company should spend. So they want to know this S value. So they should spend and then because it's in thousands, $40,000 to maximize their profit. Okay, this next problem is very similar, it just has a couple of extra pieces. So it says the revenue generated from selling gold dust is determined by the product of the price of $9 per pound and the number X of pounds of gold dust sold. R of X equals 9X. The cost to produce X pounds of gold dust is determined by the cost function. C of X equals X cubed minus 6X squared plus 15X. Then our question here is what amounts of gold dust should be sold to obtain first the maximum profit and then the maximum for loss. So I actually have two questions here. The first thing I want to notice is that we weren't given our profit equation like we were in our last problem, but we still are trying to maximize profit. So before we can do anything else, we actually have to create our profit equation using the formula profit equals your revenue, the amount you bring in, minus your cost, the amount that you've spent. So they gave us a revenue equation, R of X equals 9 times X, and they gave us a cost equation, C of X equals X cubed minus 6X squared, plus 15X. So to find our profit equation, P of X, we're actually going to subtract them, R of X minus C of X. So filling in what we have, P of X is equal to our revenue equation, which is 9X, minus, in parentheses, X cubed minus 6X squared plus 15X. And then we're just going to make sure to distribute that negative. So P of X equals 9X minus X cubed plus 6X squared minus 15X. So our profit equation, and I'm just going to write this in standard form, should be negative X cubed plus 6X squared, and then 9X minus 15X gives us that minus 6X. So I'm just going to cloud it. This is our equation that we want to maximize or to look for the maximum for loss. Once we've done that, now we can go ahead, just like we did in number 1, and look for those extrema. So to do that, we're going to take our derivative. P prime is equal to, using our power rule, negative 3x squared plus 12x minus 6. And then we want to set that equal to 0, so I'm going to bring this up top here. Taking out my GCF of negative 3, we get x squared minus 4x plus 2 equals 0. Now, this is a quadratic, so I can solve that x squared minus 4x plus 2 however I know how. Ideally, I would factor, but I actually can't factor this one. There's no factors of positive 2 that add up to negative 4. So we get to use our old friend, the quadratic formula, that negative b plus or minus the square root of b squared minus, oh my gosh, negative b plus or minus the square root of b squared minus 4ac all over 2a. How embarrassing, I almost forgot. So x equals the opposite of b, so 4 plus or minus the square root. Negative 4 squared is 16, minus 4 times 1 times 2 is 8. All over 2 times 1 is just 2. So this gives us x equals 4 plus or minus the square root of 8 over 2, which I'm going to write as 4 plus or minus 2 root 2 over 2. And then just simplifying, dividing everything by 2, we get x equals, 2 plus or minus the square root of 2. And let's just get those two values. So x equals 2 plus root 2. Using our calculator, 2 plus root 2 should give us about 3.414. And x equals 2 minus root 2. Using our calculator, that should give us about 0.586. Okay, got them. Those are our two horizontal tangents, the place where we would have either a maximum or a minimum. From there, we're going to go back to our original profit equation that we clouded and see what we get when we plug in either of those and see which one would be the maximum profit and which would be the maximum for loss. So plugging into our profit equation, 3.41, whoops. Again, plugging into this equation. Give you guys a second to grab your calculators. When you plug that in, you should get 9.657. Feel free to pause me, go ahead and try, make sure you get that. And when we plug in 0.586, we should get negative 1.657. When we do that, we notice that we have obviously one large value and one small value. So we want to answer our question, what amounts of gold dust should be sold to obtain the maximum profit and the maximum for loss, where number X is pounds of gold dust. So we would want to sell, let's put our answer in green, 3.414 pounds for maximum profit, and 0.586 pounds for maximum loss. Okay, as we move on to number 3, we are adding just one more step. So this says, suppose lowercase p of x equals 70 minus 0.01 x represents our price. So I'm just going to highlight our price equation. And then c of x equals 8,000 plus 50x plus 0.03x squared represents the cost of manufacturing widgets. And then they're telling us that x is our production level of widget units. They're asking us to find a production level, which means x, that is going to minimize our profit. Maximize our profit, whoops. And just like in the last problem, they're asking us about profit, but then they didn't give us profit. They gave us price and cost. So first we want to find our x that's going to maximize our profit. And then after that, we want to talk about the price when the maximum profit is realized. So in the last problem, they gave us revenue and cost. Here they gave us price and cost. So the first thing we have to do is actually take our price and our cost, or take our price and turn it into our revenue. So it says our revenue equation, R of x, is equal to x, the number of units, times P of x, the price. So our revenue equation, what color? R of x is equal to our number of units x, which we don't know, times P of x, which they gave us as 70 minus 0.01x. So our R of x equation, our revenue, is 70x minus 0.01x squared. Now that we found our revenue, we can take that and plug it in to find our profit equation. Our P of x is equal to R of x minus our cost, C of x. So now we can go ahead and plug in P of x equals the revenue equation we just found, 70x minus 0.01x squared, minus the cost equation they gave us, in parentheses 8,000 plus 50x plus 0.03x squared. Just make sure we distribute any negatives. So I have 70x minus 0.01x squared minus 8,000 minus 50x minus 0.03x squared. And then combining all like terms, I'm going to write my P of x equation in standard form as negative 0.04x squared Then we have 70x minus 50x gives us plus 20x minus 8,000. So finally, we found our profit equation that we want to maximize. So just extra steps at the beginning before we find that equation. From there, it's the same. We're going to go ahead and find or take our derivative p prime. Bringing our 2 down, we would get negative 0.08x plus 20, and the negative 8,000 goes away. Setting that equal to 0, negative 0.08x plus 20 equals 0. Negative 0.08x equals negative 20. So x equals negative 20 over negative 0.08. Doing that division, we get x equals 250. So we only have one value here, so our production level that's going to maximize our profit is 250. So let's write out 250. What are we selling here? Widgets. 250 widgets is our maximum production level. Then they gave us a bonus question. They said, what is the price when the maximum profit is realized? So we know if we sell 250 widgets, that's how we'll get our maximum profit. So then the question is, how much should we charge people? So the price is our lowercase p of x equation, which was 70 minus 0.01x. And we want to find the price when we're selling 250. So we have 70 minus 0.01 times 250, which gives us 67.5. So we should sell these for $67.50 per widget. Okay, number 4 is a little bit different. It says a company estimates that the cost in dollars of producing X units of a product can be modeled by, and then they give us our C of X cost equation. Oops. C equals 800 plus 0.04x plus 0.0002x squared. We want to find our production level, so again, we're looking for our X value. And then we want to minimize our average cost per unit. So they gave us C as our total cost. So to find our average cost, we need to take our total cost, C, and divide it by our number of units, which is X. So the first thing we need to do is take our equation, C, 800 plus 0.04x plus 0.0002x squared, our cost, and make it our average cost equation. So let's divide everything by x. So our average cost, let's call it our average cost, is equal to 800 over x plus 0.04, x's cancel, plus 0.0002, x squared over x just gives us x. So here's our equation that we want to minimize. So just like before, we're going to want to take our derivative, look for our extrema. However, because I have that 800 over x, I'm first just going to rewrite my equation as 800, and then I'm going to write this as x to the -1 because I think it'll make it easier when I go to take my derivative. Okay, so now that I've found that equation, we can actually go ahead and find our derivative. So whoops, let's switch this over. Our derivative is equal to -800x to the 1 less power, so -2, plus, whoops, I added an x on accident, so this goes away, and we're just left with 0.0002. Okay, go ahead, double check that. Sorry that I had accidentally added that x in there. That was an accident. Just like always, now that we have our derivative, we want to go ahead and set it equal to 0 so we can find those places where we have a horizontal tangent. So we have -800, I'm going to write this over x squared, plus 0.0002 equals 0. So we have negative 800 over x squared equals negative 0.0002. So x squared equals negative 0.0002 over negative 800. Taking the square, or dividing those, we have x squared equals. And from here we can solve using square roots. So we get x equals plus or minus 2,000. And we're obviously not going to be selling a negative 2,000 items. So our production level would be x equals positive 2,000, so 2,000 units to minimize our cost. So this one was a little bit different, or to minimize our average cost was a little bit different because we had to first take our cost equation and divide it by our total number of units. Okay, for number 5 and 6, we actually have to write our own equation. So for number 5, we're going to use multiple choice, and then for number 6, we'll actually have to write it ourselves. So the first step here is to take the information they give us and to turn it into a revenue equation. So number 5 says a flower shop sells 375 bouquets a month when it charges $30 each. For each $2 increase in price, they lose 15 customers. So which equation is going to best model that? So in order to do this, we have to remember that our revenue, R of x, is equal to our number of units times the price. So as we look here, the original information we have is our number of units is 375 and our price is 30. So we should see that in all of our equations, our number of units and then our price. So then what's happening is it says for each $2 increase in price, they lose 15 customers. So every time, if they add $2, they lose 15 customers. If they add $4, they lose 30 customers. So our X is going to represent the number of price increases, and then we have to account for how much is increasing and how many customers we're losing. So the first thing it tells us is for every $2 increase in price, oops, wrong color. For every $2 increase in price is going to affect our $30. So we're looking for the equation that has our 30 being affected by a $2 increase. So not this, not this, not this. But this plus 2x represents a $2 increase for every x. So 1x, 2x, 3x. Then it says, when that happens every time, they lose 15 customers. So hopefully in our same equation, this 375 for every x, every time they increase the price, they lose 15 customers. So we have found our revenue equation. R of x is equal to 375 minus 15x times 30 plus 2x. Once we do that, we want to determine what price the flower shop should sell a bouquet for in order to maximize their revenue. So we're going to take this R of x equation and we're going to do what we did before. We're going to find the derivative, we're going to look for the extrema, we're going to find the price where we should maximum, and then also the maximum revenue. This equation, though, is in factored form, and it's easiest for us to take the derivative in standard form. So let's go ahead and multiply this out. So multiplying 375 times 30, we should get 11,250. Foiling 375 times 2 gives us a positive 750x. On the inside, minus 15 times 30 gives us a negative 450x, and then negative 15x times positive 2x gives us a negative 30x squared. So let's go ahead and just clean that up a little bit. We have R of x equals 11,250. Combining our positive 750 and our negative 450, we get a positive 300x minus 30x squared. Now that we finally have our revenue equation, we can take our derivative to find our extrema. So let's go ahead and find our prime. Derivative of a constant goes away. Derivative of 300x is just 300, and then power rule gives us negative 60x. Setting that equal to 0, 300 minus 60x equals 0. We're left with 300 equals 60x. So x equals 300 divided by 60 should be 5. Okay, so x equals 5, but x is the number of times we're changing our price. So the first thing we want to do is determine the price. So our price, remember, was this 30 plus 2x. So 30 plus 2 times 5 gives us 30 plus 10. This tells us that we should sell $40 per bouquet. And when we do that, what will our maximum revenue actually be? So R of 5 gives us, plugging into either your original factored form or your standard form, 375 minus 15 times 5 times 30 plus 2 times 5. Multiplying this out, we should get, take a second and do it, $12,000 maximum profit. Maximum revenue. Whoops. Okay, our last problem for today, number 6, is very similar to number 5, except we have to write the equation all on our own. So it says the manager of a 100-unit apartment complex knows from experience that all units will be occupied if the rent is $800 per month. A market survey suggests that on average, one additional unit will remain vacant for every $10 increase in rent. So what rent should the manager charge to maximize revenue? And then once we figure that out, we'll determine what is the increase in monthly rental income with that new amount. So just like before, we need to come up with our revenue equation, R of X, by determining number of units sold and the price that they're selling for. In this case, the thing that we're selling are apartments. So we have a 100-unit apartment complex, and we're selling these for $800 per month. So when we start our equation, R of X, whoops, we're starting with 100 units at $800 per month, but we need to account for the change. So the market survey suggests that on average, one additional unit will remain vacant. So 1 unit less, so that's going to be minus, my highlighter, minus 1x for every time that we increase rent by $10. So that's going to be our plus $10 per change in price. So the revenue equation we've come up with is 100 minus 1x times 800 minus 10x. From there, we want to find the maximum revenue, or want to find how much we should be charging to maximize revenue. So let's go ahead and turn our factored equation into a standard form equation. So R of X equals 100 times 800 gives us 80,000 minus, 100 plus 10x gives us plus 1,000x minus 800x minus 10x squared, and then let's just go ahead and simplify that. So we have 80,000 plus 200x minus 10x squared as our revenue equation. Now let's find our extrema. So let's take our derivative r prime. 80,000 is a constant, so our derivative becomes 200 minus 20x. Setting that equal to 0. We get, equals 0, moving too fast. We get 200 equals 20x, so x equals 10. So if x is 10, then we're going to maximize our revenue. Remember though, x is the number of times we're actually changing the rent. So let's go back, and it says what rent should we actually be using? So our rent was that original $800 plus 10 for every time we change it. So our rent is 800 plus 10x. So 800 plus 10 times that x was 10 gives us 800 plus 100 gives us $900 per month to maximize revenue. So even though not all the apartments will be filled, that's how we're going to make the most amount of money. Now this last part is a little different. It says, what is the increase? The increase in monthly rental income with this new amount. So to do this, we're going to find our original monthly income, and then we'll find our new monthly income, and we'll compare them. So our original revenue would be if we had no change in our rents. That would be if we had the 100 units at $800 per month, and each month we would make $80,000. Our new income, if we make this change, would be R of 10, would be if we had that 100 minus 10 times our 800 plus 10 times 10, so 100 would be 90 times 900. So we're only selling 90 units, but we're selling them at $900 per month. And if we do that, we're making $81,000 per month. So our increase would be a $1,000 monthly income increase. It's not a bad increase. Okay, great job with the first day of optimization. Homework 39 is a handout in the optimization homework packet. If you have any questions, you can go ahead and ask your teacher.